So today's not like a formal lecture. It's more of a little demonstration. And I just thought, we covered some very, very, very basics of neural networks. And, um, I did it with just some basic matrix operations, and we had kind of the most rudimentary form of gradient descent. And I'm going to assign a homework, post a homework assignment where you're going to kind of do um, work with some neural networks, or at least write similar code where you're going to do matrix operations. And you'll do it kind of in this manual fashion, which, hopefully will be of educational value for you. But in real life, nobody would do neural networks in that way. Everybody kind of uses these formal packages, and I would say Python is probably the preferred language of choice as far as neural networks go. However, and kind of the biggest systems that are not systems, but the most popular software for neural networks would be PyTorch, which was developed by Facebook, and TensorFlow, which was developed by Google. And so these are kind of the I don't know, the titans of the industry, and they've published kind of all of their neural network code in these open source packages that you can then use and adapt and things like that. So we will take a look at TensorFlow, which the back end, as far as the calculations go. Ooh, what language is that written in? I'm not 100% sure. I want to see something else. C, maybe, I don't know. Okay, but then on top of that, these interfaces have been built, and so there's a package called Keras, and that sits on top of TensorFlow, and it allows for the kind of creation of neural networks, in a little bit of a easier fashion. Okay, and I don't want to say easy because it, just like any other package and things, just like learning dplyr, there's a whole set of vocabulary and functions and things that you've got to learn. And so anyway, you can set up TensorFlow, you can set up Keras, and you can interact with it via R. It's going to require, a Python or Anaconda installation put on your machine, especially if you have a Windows thing. And during the installation process, the installation process is a bit of a a challenge in of itself. It can be, depending on your computer. So, but I don't want to spend time going over the installation, just because your machine is probably different from mine, and what you're going to encounter will be a little bit different. But ideally, you can just install that package as TensorFlow, and it's going to do a bunch of stuff. If you've already installed Anaconda on your machine, you can kind of skip the Anaconda part. It might say like, it needs to install Miniconda or something like that.
I have a question.
Yeah, go for it.
Will we need TensorFlow and Keras for R for like our homework?
No. This is more like just for fun demo.
Okay.
Just showing that like this stuff exists. So
okay.
Yeah. So you don't stress about it. Okay. Oh, so anyway, oh yeah, it's Friday, and Data Fest starts this weekend. Are you guys doing Data Fest? Maybe some of you. Okay, some of you, yeah. Well, some of you, yes, some of you, no. So, hang on a second. Okay, so yeah, so it's Data Fest, and I signed up to be, I guess, an advisor or mentor or something. So I don't know where they publish these things, but I think I'm listed. So I'll hold kind of like a I guess, an open office hours or something tonight at like 8 p.m. And just so you know, and if you have any questions, if you want some advice or guidelines. General advice for those of you participating in DataFest is start simple and start just by exploring the data. So spend a lot of time exploring the data. Just, you know, use dplyr or whatever it is to kind of get summaries by groups and whatever. I don't know what the data is, but just start kind of slicing the data in a few different ways, and then see if there's anything kind of interesting that you noticed during your exploratory data analysis, and then move from there. Okay, and then I would say overall focus on while you're working in your group, you might find like there's, you know, several different avenues to pursue, several different ideas that you want to pursue. And I would say in the beginning, you can pursue some of these different things, but then towards the end, you want to kind of hone in on just basically one idea and center your presentation around that central idea. That's kind of my general advice, but I have no idea anything about the data or you know, what it's going to look like tonight. So but anyway, if you're participating, that's what's going on. Okay, so anyway, back to TensorFlow and Keras and all of this stuff. There's a page, tensorflow.rstudio.com, and you can go to the installation, and they've designed these packages to kind of set up to help you get TensorFlow set up on your machine. Okay, you will also need to install Keras. Okay, and so you have the R interface to Keras. Keras sits on top of TensorFlow, and that's kind of how we'll build our neural networks. So anyway, I'm just using some very, very, very basic intro demo, and then I've annotated kind of all of the lines of code, hopefully explaining what exactly is happening when we're specifying the models and things of that nature. Okay, so anyway, I'll start by loading TensorFlow and loading Keras. Okay, and there's a few built-in data sets. One of them is the MNIST handwritten digits data set. Okay, and let me just kind of show you what the structure of MNIST is. That it's a list of two, and you see you have the training, and then you have the test. The training data set, you know, has 60,000 images, and this is kind of your first tensor. So a tensor is basically an array, but it allows for it to be high dimensional. So we have matrices. So basically, a tensor is just a n-dimensional matrix, or, you know, the equivalent of an array in R. And the name TensorFlow kind of comes from the idea that, you know, you have one matrix that's being worked upon, you know, via matrix multiplication or whatever, and then it results in another matrix, and, you know, you apply activation functions and things like that. Okay, so our input matrix X, or input array X, or input tensor, there's 60,000 images, and each image is 28 by 28 pixels. Okay, so if I just do I'm sorry, MNIST $MNIST $train $X, and let's just do the first image. Okay, so one, and it's three-dimensional, so I have to put in comma, comma, two commas there. Okay, this is going to be the result. You know what? Let me shrink my text a tiny bit, okay. And you might actually be able to see the number, just because the zeros show up as black text. Or I mean, so zero would be kind of black or white, and then, you know, the large numbers too, you know, where there's ink, actually shows up almost like a thing. So you can almost kind of see the number that appears here, right? So that's image one, So that looks like a 5. Image 2 looks like a 0. So it's kind of neat seeing it in this. So there's that looks like a 4, right? Okay, so so it comes in these 28 by 28 pixel grids. Let me just reset this. Okay, and what we're going to do is we're going to just kind of divide everything by 255 to kind of get everything on the scale from 0 to 1. Okay, which is what we did when we did the kind of the demo code, I think, right? And then what we're going to do is we are going to set up a sequential model. Okay, there's a Keras supports different models, but a sequential model is kind of your standard neural network model, which basically means, you know, you start off with your input, you do something, and then you do something, and then you do something, and it just kind of forms a sequence of layers and operations. Some of the other models that Keras supports would be, you know, if you have this kind of input over here and then a different input, and then you're combining them later, and you can kind of set up your model, you know, in some other form where you have like multiple different inputs that, you know, and it gets a little, you know, you can make fairly complicated things. So anyway, just I've included a bunch of kind of links to some of the reference pages. So this is the regular Keras reference for the sequential model, and then there's also the Keras for RStudio reference. The Keras for RStudio reference in some places are very bare bones. So you'd have to go to the kind of the primary Keras thing, which as far as the main Keras webpage goes, it's written in Python code, but thankfully the calls to the functions are almost identical, whether you're using Python or R. You know, obviously a couple things are going to be different, but as far as the arguments that get passed into Keras and get passed into R, you know, via RStudio or R will be similar. Okay. So here we initialize a model, okay, and we just say, hey, we're going to set up a sequential model, and then what we do is we write out what kind of layers that we're going to have, okay. And so the first thing we're going to do, and you don't have to do this, but just to kind of get us in a similar form of what we did in the example where we were using matrices, is we're going to flatten the input values, right? So our inputs are coming into this 28 by 28 matrix, and basically what we're going to do is we're going to just kind of flatten it to be a 1 by 784 vector, okay? And so that's what this first layer underscore flatten goes, okay? And so there's all kinds of different layers that you can use in Keras, okay? And under the Keras reference, so on the primary thing, you can click the layers API, and it kind of gives you a whole bunch of different types of layers that can be added, okay? And and you can read all of these things, all right? But basically the first layer that we have here is layer flatten. Is going to take that 28 by 28, flatten it into a 1 by 784 or 784 by 1. Okay. And then the layer dense is what's known as a densely connected or a fully connected neural network layer. Okay, that's the idea that every node in the previous layer is going to be connected to every node in the dense layer. Okay, so it's densely connected, fully connected. Those are those are synonyms, and every node from the previous layer is connected to every node in this layer. Okay, and so here you specify some kind of arbitrary number. You can say, you know, I just want I don't know, here arbitrarily I'm just following the tutorial code. The tutorial code said, you know, let's use 128 nodes. Okay, I think in my example in class, I used 30 nodes in the hidden layer, whatever you want to do, right? If you want to have additional layers, if you wanted to have a second layer, you can just add a second layer just like that, okay? And so, but here, I'm just kind of keeping it simple. We'll have one fully connected layer. And within the dense layer, you can specify the activation function. You can say, I want the rectified linear activation function. So, in our class, we in my demo, I use the sigmoid function, okay? But you can specify any of these things. You can also specify the activation as its own layer, right? So they can be done in the they can be done in the dense layer. In the dense layer, you can specify the activation, okay? Or you can specify the activation as its own layer. And so, however you want to do it, right? You can specify the activation. And all we're doing is we're just saying, it goes from the previous layer to the next layer, okay? And so we're going to specify an activation function, or activation function. In our case, the ReLU. And then we can specify a dropout layer, okay? Dropout, let me just illustrate what a dropout is. Dropout artificially takes some of the nodes and it will set them to 0, okay? So this is kind of, these are densely connected or fully connected neural network layers, okay? And so every node here is connected to the next node, right? And what dropout does is it just says, you know what, we're going to just randomly select some of these nodes and we're going to just set them to 0, okay? And effectively, when you set a node to 0, it effectively kills all of the connections from the previous layer and kills all of the connections going to the next layer, okay? Now, why would we want to do something like that, okay? Dropout is a way to help avoid overfitting, okay? By, if you have every single node connected to the next node, it's going to basically, every adjustment, on this node right here, every adjustment here is going to play a small role in, whatever prediction we make at the end, right? So if I make an adjustment here, it's going to play a small role in every single node here, and it's going to effectively affect the final output layer, okay? And that's fine, but basically every single input image is going to, every input gets connected to here, and this is going to get adjusted, and it's going to influence everything out, okay? When you apply dropout, basically the dropout happens randomly, and therefore, some of the images will affect. It's kind of just, it's like saying, we'll use some of the images during our training of this node, but not every single one, okay? And so that's going to kind of just artificially not use the entire training set, but just only use a subset of it, which can improve, in some cases, can improve performance by reducing the chance of overfitting. Okay, so here, just arbitrarily, we're saying use a dropout of 20%, which means 20% of the nodes are going to get set to 0. And you can adjust this anywhere from 0 to, well, you don't want to do 100%, but values under 0.5 probably a little bit more. Okay, and then finally we have the output layer. Okay, and this is going to go to our output layer, and that's going to be a densely connected. Question, is dropout like cross-validation? It's not quite like cross-validation. It's just a little bit more like subsetting, randomized subsetting, I would say. Okay. And then finally, for the output, we're going to make predictions. Okay, and if you take a look at the structure of MNIST, okay, we have the output is a label, okay? But we're going to set up 10 output nodes, okay? And the softmax, the softmax activation is used to oftentimes for classification models, okay? And basically what the softmax is let me just take you to the Wikipedia page on softmax, is we're going to have 10 nodes in the output layer. You're going to take the output, raise e to that number, whatever it is. So the outputs can be anywhere from I guess well, with the rectified linear, it's going to be anywhere from 0 to infinity, but it could also take negative values as well. And so you're going to raise e to some number. It's going to get huge, okay? And then other value, and you do this for every single category, right? So maybe 5 has a value of 100, okay? 6 has a value of 20, 7 has a value of 3, 8 has a value of 1 or something, okay? You're going to raise e to every single one of these powers, and then you're going to sum them up, okay? So this sum could be something extraordinarily huge or small. But anyway, basically what's going to happen is it's going to reduce the output. The output value is going to be between 0 and 1 for everything. And the sum of all of the outputs will add up to 1, okay? So that's what's called a softmax. And it's a simple function. It's used for classification. Okay, so this is it. This is the specification of the model. If we wanted to specify a different model, like the one we, so I'm gonna comment this out, but if I want to, I could do sigmoid, I could do 30, and this would be a lot more similar to, actually, sigmoid here. Okay, this would be a lot more similar to kind of the model that we created in Monday's lecture. Okay, but all right. So anyway, that's how you specify a model. You just kind of list them off. If you're interested in using Keras or anything like that, I just strongly encourage you to take a look at some of the examples that you might see, and they're just kind of listed off here. So you have a dense activation, things of that nature. So we have that. Okay. All right, so I'll go ahead and I'll set up my model here. So I'll run this. Whoops. Specify the model and specify the model, and then you can ask for the summary of the model. And the summary of the model just kind of gives you a little bit of the structure. All right. And here it says, okay, the first one, the model, the output's going to be 784 nodes coming in that layer. Okay. And then you have a dense layer. And the output of that, because we have 128 nodes in the dense layer, the output's going to be length 128. And this is how many parameters need to be estimated, okay? And this is going to be, because every node in the previous layer is connected to every node here, this is the result of 784 times 128, okay? So every weight from the previous layer to this layer, plus you have a bias term for every single one of these things, okay? You can also, and that's how they get this number, 100,480, okay? So that's how you can specify the thing. If you want no biases, I think you can do, let me just double check the reference. You can specify whether you do or do not want biases, but probably, where is my thing? Okay, dense layer, use bias, we can do use underscore bias false if we wanted to. Now, probably we should use biases, but if we did this, then did I do something wrong? Model here. sorry. Oh, I'm sorry. I kept adding. Okay. So here's the initial model. We're going to initialize that. Here's the model, and then we'll pass a summary on the model. And here, the number of parameters to estimate now is just 784 times 128. But I do want the biases, so I will specify it with the bias. So let me reinitialize my model, specify it as such. The summary, and we get that. Okay. And then finally, it also shows you the number of parameters to estimate between the model and the output, the input and the output model. And there's, again, 128 by 10 is 1,280 plus the biases, 1,290 parameters to estimate. Okay. And it lists off the parameters here just in case in your design, it's possible that you end up something with like 10 billion parameters to estimate, and you realize, oh, you know what? This model might have a few too many parameters to estimate, and we're going to overfit, right? So, because I have about 60,000 images, right? And if I have more parameters than input images, you know, we run the risk of overfitting and things like that. And so there's always some kind of risk, okay? Because I've got so many parameters, but that's fine, okay? Now to fit the model, we have to run a compile and we run a fit, okay? Now these are come directly from the Keras training API, okay? Keras API. So if you follow that link, it will talk about the APIs, you know, how to interact with the Keras model. And so you have the compile method and you have the fit method. Okay, compile basically specifies a few other things as far as how we are going to train our model. Okay, so here in the model specification, we specified the layers. Okay, and then for the compiling part, you're going to specify how are you measuring loss. Okay, in class, the way we measured loss was using the mean squared error. We just said, you know, take, 0, 1, take the difference, measure the squared error, okay? You have a few different choices for the loss function, okay? So if you, I have that linked here, okay? So there's all sorts of ways to measure loss, okay? So, you know, for regression type problems, mean squared error is probably your most common choice, but you can also do a bunch of other things, mean absolute error, mean absolute percentage error, things like that, mean squared logarithm, things like that, okay? And as far as things for categorical variables, there's a few different choices. You have the binary cross entropy, the categorical cross entropy, and so maybe, I don't know if you'll talk about these different kinds of ways to measure error in 101C, but there's a whole bunch of stuff, you know, Kublak-Leibler, divergence. Okay, and you can click any of these things. There's often just a very brief description on the scenario in which you would use this particular type of loss, and then you'll see in here name equals, and then there will be some kind of string that we would use. So in our case, we're going to use the sparse categorical cross entropy, and it says use this cross entropy loss function when there are 2 or more label classes, which is what we have here. We have 10 label classes and things like that. Okay, and it talks about, you know, if you have different kinds of representation, one hot representation, meaning if you convert everything to zeros and ones, you can use the categorical cross entropy loss, things of that nature. Okay, so we specify our loss function, mean squared error, or some kind of categorical loss function. We can also specify how to optimize it. Okay, and again, consult the reference. Okay, and so as far as the different optimizers go, you have gradient descent, which is SGD, okay? And then everything else here is some version of gradient descent, but has been tweaked for better performance, okay? And so you have eta grad, which is the eta grad algorithm. It's another kind of gradient descent thing. Atom is another gradient descent. This is Atom optimization is a stochastic gradient descent method that is based on adaptive estimation of first order and second order moments. I have no idea what that sentence even means, but apparently, it performs well. And you can try some of these things. Sometimes, a lot of times you can just kind of stick with one and it will work, but then maybe depending on your model, it has trouble performing or something, and you can try switching your optimizer. And sometimes switching the optimizer fixes the trick, or it could just be your model's poorly specified. There's all sorts of things as far as why something could break. So who knows? Okay, and then finally, you can also specify, how you want to measure your performance. Okay, so you can specify metrics, and in our case, we're going to use the accuracy. Okay, so we will go ahead and compile the model, right? And then now we're going to fit the model, okay? And so fitting the model says, okay, here's my training data, and I want you to run this many iterations. And if you want to do some kind of validation thing, you can do that as well, okay? And so what we have specified here is, as far as fitting the model, we're going to say, all right, the training data, we're going to use the training data X and the training data Y, okay? An epoch is how many times you should cycle through all of your training cases. So I have 60,000 images. And so if I just do one epoch, it says just go through all 60,000 images once, okay? Here I'm going to say go through all 60,000 images 5 times, okay? So we're going to go through all 60,000 images 5 different times, and that's going to be an epoch. You can specify more or less, obviously more epochs will take more time. The validation split here is a little bit like cross-validation, but not formally so. It's basically at the start of each epoch, or not at the start of each, I think at the very beginning, very beginning, it just does a training validation split. So here we're going to say take 30% of the 60,000 images and put it into a validation set. So we have our 60,000 training images. We're going to split it into 42,000 and 18,000. And we're going to set the 18,000 aside. We're going to use the training data to fit the model. And then at the end of each epoch, we run a validation. We're going to kind of make our predictions based on the 18,000, and we will get a measure of its performance. And you will see in the plot, you will get the training error. So how much error do we have on the training data? And then it will also get a measure of how much error we get on those 18,000 validation data sets, right? And so this is kind of a, you specify some number here. Verbose will give you basically a progress bar for the, as it's fitting, right? So, this is a simple data set, not simple, but just the MNIST is so clean, and it kind of can process through it fairly quickly. But in some cases, training your data on some million image data set can take hours on your computer. And so the verbose part will give you basically some progress bar information. Okay, so I'm going to go ahead and run this, and this will take a couple of seconds on my computer here, okay? And you'll see it running, okay? So here is the fit, right? And so this is a measure of the loss and the accuracy. This is on the training, and then with each epoch, it shows us basically how much our validation set improves, okay? So as we continue running, modeling our data, we can see the loss function, which is our whatever cross sparse categorical cross entropy, okay? That continues to decline, but our validation error, or our validation loss, it doesn't change too much from the fourth and fifth epoch, okay? And then we see a similar type of thing regarding the accuracy, which is just another metric, how accurately are we performing? With our validation data, we achieve around 97% accuracy, and it seems just 96, 97% seems to be fairly stable after the third or fourth epoch. Whereas with our training data, it continues to improve as we run more and more epochs. Okay. And then from there, you can run your predictions, right? So now you have a model, you can use it to predict on kind of your test cases, okay? And then, and so here, these are kind of this is the predictions. This is, let me just go ahead and I'll round this, round to say 2 decimal places. Yeah, we'll just round to 1. Okay, or 0. And so we can say, all right, the first one we're predicting, out of our 10 nodes, we're predicting basically 7 and 2 and so on, and we're predicting all sorts of things, okay? And then you can run an overall evaluation on the model, and it says, okay, your accuracy for the test data, we've achieved around 97% accuracy using this kind of simple, fairly simple model that we've created using TensorFlow and Keras, okay? There are a few more examples that, if this kind of stuff is interesting to you, you can check it out. There's a few more tutorials here. I basically followed this basic, the quick start tutorial here. And I've just in my code, or I've added a few more comments to kind of expand on each of these things, just because this tutorial here is very kind of bare bones, okay? But you can see a few more things. You've got an image classification data set, okay? And in here you can try to classify the different kinds of, they have images of clothing, right? And so this, you would say, okay, that's a boot. And I think you've got the fashion MNIST. What does it have? There's a bunch of different things. Okay, but anyway, this is kind of a similar thing where you have 28 by 28 pixel images, and you're supposed to say that's a sweater, and that's a coat, and that's a t-shirt, and that's a shoe, and that's a boot, and things like that. Okay. Other examples, the Boston housing prices data set, text classification, things of that nature. I totally forgot about view quizzes today, huh? All right, well, I guess I'll just give you all 3 answers right now. Okay, what is today? 4th week Friday? 4th week Friday, all right, B, C, and D. So B, C, D, so bear, cat, dog. Bear, cat, dog. For your 3 view quiz answers for today. Okay, well, anyway, that's just, oh, it says the quiz is not available. Oh, that's because, yeah, I generally make it not available until, let me fix this up here. And 5 p.m. Okay, so we will do that. Okay, it should be fixed now. You should be able to take the quiz. Bear, cat, dog. Okay, and so this is just a simple kind of demo regarding Keras and TensorFlow, just in case it's something you want to kind of play around and get started with. Not really a formal lecture. I'm not going to put any of this stuff on exams or anything like that. But I imagine some of you are kind of curious about doing a little bit more with neural networks. And so hopefully this is just enough to get started, and at least pointing you to the reference resources that you'll definitely need to do anything. And there's a lot to read. There's a lot of tutorials out there, and not every tutorial is great. So just be careful, okay? I would say start with clean data sets, okay? If you want to play around with Keras, start with some clean data sets like the MNIST data set, the fashion MNIST data set is also a very clean data set. And some of these other examples are in these tutorials are clean. And then once you feel comfortable, then you can go on to places like Kaggle and take data sets from there. But be careful, just because on Kaggle, there are a ton of botched, messed up data sets where people did some web scraping, but when I go through the data, I think they did a bad job with the web scraping. And so the resulting data is just full of duplicates or full of things in the wrong categories and wrong columns, or just poorly formatted, where some of the columns should have multiple things, right? I think I've seen a data set like movies data set, and a lot of times a movie will have multiple genre categories, right? It'll be like an adventure movie slash a romance movie slash action or something like that. And then, but for whatever reason in the data set, they just picked the first thing, the first one out of maybe like 3 categories, or it might be like or this movie stars so and so, and they'll pick only just the first one. And I don't know how they pick the first one, and it could be alphabetical or something, but definitely those types of things are problematic. So or like where was the movie produced or filmed? And a lot of movies have multiple locations, multiple things. And so so if there's only like one per column, that could definitely be problematic. And I understand the desire to reduce everything to one value, but who's the I don't know, but you think of like the Harry Potter movies, and what's the who does it star? I guess Daniel Radcliffe would be number 1, but then you also have Hermione and Ron, and who knows. So but so anyway, just be careful. Always pick a data set where you're a little bit familiar with the subject matter, so that when you go through a few of the lines, and you should definitely go through some of the lines line by line, you can say, okay, this data seems accurate, or this data is definitely missing some information. Okay, we'll end here, and have a good weekend, you guys. We'll see you guys on Monday. And if you're competing in Data Fest, good luck, and have fun out there. And if you're on Data Fest, feel free to stop by, I guess, my open sessions, and we'll see you then. All right, have a good night, you guys. Have a good weekend.